our table. Yeah. No. The rod is rotating about a fixed axis. And this is also known as the instantaneous center. So there's no velocity component. The center of gravity has a velocity, but it's taken over by V equal to omega R. So it's rotating about a fixed axis. So you only need to consider T2, which is consider I A omega squared. It's not a general motion. There's no linear motion. General motion, then you have to consider what? The V. Does that answer your question or no? If it's general motion, if you go back to over here, if you go back to this lecture over here, or one further back, hold on. So now we are rotating from here as a fixed axis. Yeah, this rotation over here have the rigid bodies are about a fixed point O, has both translation and rotation. Fixed point. At point G, oh, I think you're right. I think you're right. I got it wrong. My bad. Wait. Let me look at this. When the rod is rotating, translation. Hold on. Don't move yet. Wait. Don't do anything yet. If I were to finalize this equation to T is equal to, hold on, it's my bad, okay? It's my bad for this, it's not you, okay? So if we have 0.5 here, and then we have our omega squared taken out, and if I were to do this, this is equal to, this will be equal to M RG squared plus by IG 0.5 plus by IG. It's the same expression over there. Can you see that? It is. So IG MR squared, which I've taken earlier. Okay, so if I simplify this equation, it's the same as this over here. And this will be in term the same. So this is in fact our IA in our example down here. So if you look over here, this is our IA omega squared. Yes or no? Okay, thank you for clarifying with that. Okay, it's not, there's no velocity, but because. So basically, I've done this. Okay, that consider the linear velocity also. Okay, right. Are you all clear or you're confused as hell? Oh shit, some of you are smiling. Are you okay? Okay, so from here, you will have your T2 is equal to half IA omega squared. So you got your half, and then you got your A, and you got your omega squared. Okay, so therefore, oh, someone want to put up her hand. Sorry, I forgot about you. Yes. Yeah. Say it again. The T is kinetic energy. Work done is U. The work done in U, we consider the rod the spring and the applied moment. Nothing to do with kinetic energy. Yeah. I just derived the formula over here. You see this expression over here? It has a linear velocity, so I just simplify it over here, and that is the outcome. Yep, the answer will still be the same. Yeah, the answer will still exactly be the same. So from here, we have omega. So now to write out, you have T1. Are we okay, or there's something that you're not clear? Okay, then you will have plus by summation U1 to 2, and then you have T2. So this is 0, and this is equal to 7, not equal, plus. So the plus 7.854 that we consider is due to the spring. Is it the spring? Let me check. 7.854, sorry, is the moment. Then we consider the rod, which is 13.465. And then we minus by the spring. And then this whole thing is equal to half 1.875 and omega squared. So from here, omega will be equal to 7.854 plus a 30.461 minus 1.5072. 19.812 divide by 0.5 times 0.4. 0.9375. 4.59 or 4.6 radians per second. Okay. So the only difference from the example here compared to Friday is this one includes the spring force and it's not any more harder. Are we clear? Okay. Now the last section is very similar to what we have learned before. Nothing really new. Okay. And this is based on conservation of energy. So conservation of energy is basically equal to T1 plus by V1 is equal to T2 plus by what? V2. So this is the root equation that you have to comply to, conservation of energy, where T is the kinetic energy, V, I know, is the what? Is the potential energy. Okay. So 1 and 2 are, or just put subscript 1 and 2 are the initial and final positions. Okay, so 1 and 2. So-called, I don't know how true is this yet. Okay, so the conservation of, so this is the only formula that you need to know. Okay, so the conservation of energy approach is easier when compared to the principle of work and energy. So the principle of work and energy, I'll show you on the other side. The principle of work and energy. The formula is all very similar. So what we have is T1 plus by summation of work done from 1.1 to 0.2. This is equal to 2. Okay. So you can see the difference. Okay. So this method this approach is dependent on the initial and final position of the object. So typical forces encountered. So there are two typical forces. Encountered in dynamics, which you guys know already. So in dynamics, we have what? Gravitational forces, i.e. the weight, and usually such technique you have what? Elastic what? Forces. So elastic forces are spring force or your springs. Okay. So you have to remember in I think in thermodynamics or fluid mechanics, which you will learn later, the conservation of energy, criteria is energy in must be equal to energy what? Okay, this is a well-known rule. Do not change them. Okay. So if we look at gravitational potential energy, and there's a diagram that I used, I think was last week. Let me look for where the diagram is. Yeah, it's on Thursday. So if I could draw your attention, can you all get this diagram? Okay, it is on Thursday notes. Okay. So Vg is equal to what? Is equal to W YG, okay, or YG over here. And you have to take note the height, right? The height is taken from the center of gravity again. Okay, so if you have any complex body to analyze, make sure you know where the center of gravity is. Okay. So the gravitational, now one thing to take note is the sign. Okay, so the gravitational important, I'm going to put star down here, is the gravitational potential energy is positive when Yg is positive. Yg is positive since the weight has the ability to do positive work. Okay, but does not mean you can overeat. Are you clear? Are we clear? Not like me. Okay, I overeat. Okay. Okay. When the body is moved back to the datum. So in any problem, you have to